Good afternoon. This is Math 2414. It's April the 11th. This lecture is being posted at 1:30 today instead of at 7 o'clock. And it doesn't really matter to you, I guess, if you're just watching the recorded version of this. A couple of announcements here. Office hours. I want to make sure that you're aware that I'll be available online on Sundays and Tuesdays from 8:30 to 9:30, and on Tuesday, Wednesday, and Thursday from 11 to noon. I'm always available in my WebEx office during those hours. Don't hesitate to come by for help as we head into exam 3. On campus, I'll be on campus April 18th and 19th. 18th from 4 to 6 and the 19th from 9:30 to 11. Come on by. I'll be happy to help you out as you're getting ready for exam 3. Exam 3, some announcements there. The review was posted earlier today, so you have a good review online. Please take advantage of that. The window is open for exam 3 from April the 19th through the 24th. I do want to emphasize that it is your responsibility to get to a center with enough time to take the exam. And so pay attention to the hours that the testing center you're using is open. They will not give you the test if it's an hour or less left, and you really need to allow yourself a good 2 to 2.5 hours for sure to take this test, just to make sure that you have enough time to take it. I would allow 3 hours just to make sure that you have enough time. I'm going to give you 3 hours to take the test. Make sure you know the calculator policies of the center you're using. There were some issues in both cases with students and times at the testing center and with calculator policies. So I just want to emphasize to you again that this is totally your responsibility to make sure that you've got that stuff straightened out for your own particular situation, that you're aware of the policies. All right, homework. I did send out a worksheet on series and convergence of series yesterday through Remind, so make sure that you look for that. I will also post that probably on my Google site sometime today or tomorrow. There are 18 problems on that worksheet. I'll pick a few of these up on April the 15th. That will be your weekly homework this week. And when I say a few, 2 to 4 of those problems I'll probably pick up. I will send you a remind message on Saturday as to which ones I'm going to pick up. And then the key for that exam, or for that worksheet rather, will be posted on Monday, April the 16th. That worksheet is also part of your review for this test. So it is an important worksheet to go through and work on those problems. All right, so we are in the middle of talking about the convergence of infinite series. And so today our objective is going to be to talk about the alternating series test. So far, all of the series that we have looked at have been series of positive terms, and so we are going to turn our attention for a while at least on series that alternate between positive and negative terms. And then we'll also talk a little bit about the difference between conditional convergence and absolute convergence. And then we will talk about the ratio test, which is a powerful test for deciding on the convergence of a series, and it's especially useful when you have factorials in the nth term of the series. So it's especially useful for factorials, and we will be looking at series at the end of this chapter. The most important series that we look at frequently use factorials as part of their nth term. So the ratio test is actually an important test there. We'll ever so briefly mention the root test, but the ratio test is going to be our primary objective out of that section. And so this, in your textbook, by the way, this is section 5.5, and ratio test is section 5.6. All right, so that's our objective for the day today, for our lesson today. And so let's get started. So far, with convergence of series, we have talked about these things: convergence of infinite series, we have talked about geometric series, and so you definitely need to be able to recognize a geometric series when you see one. Remember, the geometric series, the general form is like this, and what basically, when you're looking at a constant raised to a function of n power, you're likely looking at a geometric series, or a good chance that you are. So that's a geometric series. We've looked at telescoping series. Telescoping series typically would be written so that the general nth term has two terms, or you could break it into two terms, usually kind of looking like this, a sub n minus a sub n plus 1, something like that. And in these problems, you're actually able to look at the nth term of the sequence of partial sums and find the limit of the nth term of the sequence of partial sums. So a telescoping series, you actually, because this is unusual, you actually look at the limit as n goes to infinity of s sub n, and remember that's the nth term of the sequence of partial sums. Don't forget that the sequence of partial sums is the sequence that you generate when you add more and more and more terms together in the series. All right, so we've looked at geometric series, looked at telescoping series. We've looked at the nth term test. The nth term test for divergence. And we've seen that in the nth term test for divergence, that if you have a series with an nth term of a sub n, and you can show that the limit as n goes to infinity of the nth term does not equal 0, then you can conclude that that series diverges. Also, don't forget at this point, don't forget, and I've mentioned this several times, if you show that the limit as n goes to infinity of the nth term of a series does go to 0, you have absolutely proved nothing. You've shown nothing. That doesn't mean anything. So this proves nothing. So don't try that on a test. It will never get you anywhere to show that the nth term goes to 0, because some convergent series, some divergent series have an nth term that goes to 0. All convergent series have an nth term that goes to 0, but some divergent series also have an nth term that goes to 0. All right, and then we've looked at the integral test, which is kind of a specialized test for convergence. But it's useful when you have expressions where no other test works. I guess it's probably basically one way to say that. We've looked at p-series. Remember, a p-series is a series that's in the form 1 over n to the p as n goes from 1 to infinity. And we've seen that if p is greater than 1, the series converges, if you do have a p-series. And if p is between 0 and 1, including 1, then the series diverges. P-series are useful when you're talking about the limit comparison test, which is the last test. And we've got the limit comparison test. We talked about the comparison test also, but I'm not going to ask you questions specifically about the comparison test. So with the limit comparison test, remember you're looking at the limit as n goes to infinity of the ratio of two series, right? You're given two series of a sub n's and b sub n's, and one of those series is known, right? And in other words, when I say it's known whether it converges or diverges. So you compare your unknown series to the known series, and basically the idea is that if you get an answer here, both series do the same thing. And don't forget, we've also looked at what happens if you get infinity or 0 as the answer, and sometimes infinity or 0 will also allow you to make a conclusion on a limit comparison test. And we talked about that at length in the last lecture, so that's a place you need to go back to and look at if you're having some questions there. All right, so here's where we are. We've done geometric, telescoping, nth term test, the integral test, p-series, and the limit comparison test. Right, and so those, the worksheet that I sent out to everybody yesterday involves those tests right there, as well as the alternating series test, which we're about to write down, but not the ratio test, which is also something we're about to talk about. All right, so let's talk about alternating series. So that's probably overall our primary objective today is to talk about alternating series. So an alternating series, basically, one way to look at this is if you have a series where the terms alternate, plus, minus, etc., or minus, plus, etc., like that. You're talking about an alternating series. And the most common forms to see, not the only forms, but the most common forms that you'll see an alternating series written would be something along these lines. The sum as n goes from 1 to infinity of -1 to the n times a sub n, right? So that a sub n is still the general nth term, and that power of -1 is what makes the series alternate, right? And as n is odd, it's obviously negative. If n is even, it's going to be positive. Or another way you'll see this written is the sum as n goes from 1 to infinity of -1 to the n plus 1 times a sub n. Now there are variations, but those are the most common ways that you're going to see that. And the first one alternates minus, plus. Second one alternates plus, minus, etc. All right, so that's the type of series we are looking at. So we're going to start this out by looking at a theorem that's actually important for what we're doing. The theorem goes like this, that if the sum as n goes from 1 to infinity of the absolute value of a sub n converges, then what must happen, then the sum as n goes from 1 to infinity of a sub n must also converge. Right. So in other words, if you take an alternating series, that's basically the idea here. Is if you take an alternating series and you take all the terms and make them positive, that's the series of absolute values, and that series converges, then the original series has to converge also. But that's what we're talking about. So an example of that little theorem right there would go along these lines. So let's look at an example of that, what I'm talking about there. Let's say we have this alternating series. The sum as n goes from 1 to infinity of -1 to the n plus 1 times 1 over n cubed, right? That's our general nth term right there. -1 to the n plus 1 times 1 over n cubed. All right, so what I want you to do is look at the series of absolute values here. The series of absolute values for this particular problem is this series, because what's going to happen there is the -1 to the n plus 1, that factor will disappear as a factor because all the terms will become positive. And so the series of absolute values is actually this series right here. The sum as n goes from 1 to infinity of 1 over n cubed. Right? And that is a convergent p-series. This is a convergent p-series. So the series of absolute values converges for this particular problem. So by the theorem that we've stated at the top, since the sum as n goes from 1 to infinity of 1 over n cubed converges, right? That's the series of absolute values right there. Since that series converges, then it must be true that the sum as n goes from 1 to infinity of -1 to the n plus 1 times 1 over n cubed, that series converges also. Since the series of absolute values converges, then the original series has to converge as well. That's what that theorem is stating. And so in this particular series, that theorem would actually be true, right? That would apply in this case. All right, so now we need to kind of elaborate on this a little bit. So we're going to make some definitions here and another theorem or two to kind of relate to this. A series is absolutely convergent. That we're defining that term here. It's absolutely convergent. So a sub n, the sum as n goes from 1 to infinity of a sub n converges absolutely if the sum as n goes from 1 to infinity of the absolute values converge. So if you get this, if you take a series, so we're going to apply this to alternating series, but if you take a series and you look at the series of absolute values, and that series converges, then the original series converges absolutely. Right? And this is in some ways you can say that this is a stronger form of convergence. And really, ultimately, what this is talking about is if you were to rearrange the terms in the series, no matter how you rearrange the terms of an absolutely convergent series, no matter how you rearrange the terms of an absolutely convergent series, the series always converges to the same number. So that is the property that we're really the most interested in here is for absolute convergence, is that you can take an absolutely convergent series and you can go and mess with the terms and rearrange them in any kind of regular or irregular fashion that you want. And no matter how you rearrange them, it will always be true that that series converges to the same, and I said to the same number, to the same problem, but it should be to the same number. Let me erase that last word. All right, and so conditionally convergent is in some ways a weaker form of convergence, and a series is conditionally convergent if the original series converges, but the series of absolute values diverges. Right, so the original series converges, but the series of absolute values diverges. All right, so that is a weaker form of convergence. And for conditionally, so this is a weaker form of convergence. And the way this works is a series that's conditionally convergent can be made to converge to different numbers. Interesting. By rearranging the terms. Now, we actually don't have enough time to go through that process of actually rearranging the terms and showing you how you can make a conditionally convergent series converge to different numbers, but easy for you to look in your textbook or look online and you can find lots of examples of a conditionally convergent series and how the series, you can creatively rearrange the terms and make the series converge to different numbers. So it always converges, but it can be made to converge to different numbers. All right, so what we have here basically is, and we're going to write this at the bottom of the page here, it goes like this. If the sum of the a sub n's converges, if you have a series that converges and the series of absolute values converges, then you have that the original series converges absolutely. So it's absolutely convergent. So it all has to do with the series of absolute values. If, on the other hand, the series of absolute values diverges, then the original series conditionally converges. All right, so now the beginning part, that if the series of a sub n's converges, how would you look at that in a case where you have a alternating series? And that's where the alternating series test comes into play. And so that's what we want to look at next. And then we're going to kind of piece together how we're going to, kind of a big picture of how we're going to deal with conditional and absolute convergence. All right, so the alternating series test obviously only applies to alternating series. And with the alternating series test, I will allow you to abbreviate that just as AST. So if you ever cite the alternating series test as a reason for something, you can just refer to it as AST. And so it goes like this. Let a sub n always be positive. Then these two series, the sum as n goes from 1 to infinity of -1 to the n times a sub n, and which is an alternating series, right? And the sum as n goes from 1 to infinity of -1 to the n plus 1 times a sub n converge. Both of those series, both of those alternating series would converge if the following two statements are true. Number one, the limit as n goes to infinity of a sub n is equal to 0. And 2, that a sub n plus 1 is less than or equal to a sub n for all n greater than or equal to 1. Now, I put greater than or equal to 1, but technically this could actually be n greater than or equal to some capital N. Basically, the idea is if eventually it happens, then this condition is satisfied. Now, the question will be, how do you, what's the convenient way to show that? And so that's what we'll look at here. All right, so so there's the alternating series test. That's a test that applies to an alternating series that is either in this form right here or in this form right here. Right, those are the two forms that we're looking at. And I've got -1 to the n plus 1. It could be -1 to the n minus 1. As long as it alternates, you're going to be okay there. And the theorem would apply. All right. So let's draw a line across the page here, and let's look at some examples here. So we're going to start off with the series that looks like this. The sum as n goes from 1 to infinity of -1 to the n plus 1 times 1 over n. Now, 1 over n by itself is called the harmonic series. This is sometimes called the alternating harmonic series. This is called the alternating harmonic series. Now, we know that the harmonic series diverges. It's a divergent p-series. So let's have a look at the alternating harmonic series. So if we looked at the alternating series test, so let's use the alternating series test here. then condition 1 is that the limit as n goes to infinity of a sub n has got to be equal to 0, right? And so now a sub n in our problem here is going to be 1 over n, right? That's a sub n in this case. So what do we have here? That the limit as n goes to infinity of 1 over n is equal to 0, and that is certainly true. So condition 1 is satisfied for the alternating series test. Condition 2, we need to show that a sub n plus 1 is less than or equal to a sub n. And you can get by showing this by either using algebra or by using calculus, right? So now we want to show that a sub n plus 1 is less than or equal to a sub n. With algebra, you're trying to show that what's a sub n plus 1 is 1 over n plus 1. You're trying to show this statement here that 1 over n plus 1 is less than or equal to 1 over n. Well, what would have to be true? The argument was a simple argument. You just simply say, using algebra, you simply say that n plus 1 is greater than or equal to n. That has to be true. In fact, it has to be greater than. And so, because when you add 1 to a number, you make it bigger, right? And so what are you going to do? You look at the reciprocal then, and the reciprocal's got to be smaller. Boom, and you're done. So that's a way of using algebra to show that 1 over n plus 1 is less than or equal to 1 over n. A very simple algebraic argument. With calculus, you simply create the function f of x equals 1 over x, which agrees with our function 1 over n whenever x happens to be a counting number. Then what do you have here? That f prime of x is negative 1 over x squared. And what do we have here? That f prime of x is negative for all x greater than or equal to 1, certainly. And so that proves that that function is decreasing, and that means that a sub n plus 1 has got to be less than or equal to a sub n. So that condition is satisfied right there. So either way you show it in a case like this, algebra or calculus, either way is okay. And so what can we say here? By the alternating series test, this series converges. Now we are not using the alternating series test. We are not able to address the question about whether this converges absolutely or conditionally. If you want to look at whether it's absolute or conditional convergence, then you would have to look at the series of absolute values. So we could do that. We could put that, I could kind of separate that out in a red box right here. And so we could say conditional or absolute, right? We know it converges. Which one is it, conditional or absolute? And so we look at the series of absolute values. And when we look at the series of absolute values in this particular problem, that would be the sum as n goes from 1 to infinity of 1 over n, right? The negative 1 as a factor drops out, and we know that that's a harmonic series. That's harmonic, and we know that that diverges. And so what do we have here? So we know that the original series, the series of absolute values diverges. The series of absolute values diverges then. But what did we also show? By the AST, we showed that the original series converged. Right? The original alternating harmonic series converged. And so what do we get here? We get conditional convergence. So the alternating harmonic series converges, but it converges conditionally, which means you could actually go through and rearrange the terms on the alternating harmonic series, and you could show that it is conditionally convergent. All right, so now let's kind of step back here for a second. you got a couple of questions here. If your question is this, if the question is, and by the way, we're talking about alternating series here, right? So we're talking about alternating series. If the question is, does series converge? Question mark. Does the series converge? Then use the alternating series test automatically. Use alternating series test to answer the question. On the other hand, if the question's a different question, if the question is, does this series conditionally converge? Let's just say conditional, absolute convergence, or diverge. If that is the question, does the series converge conditionally, absolutely, or does it diverge? Then what you need to do is you kind of go through this flow chart. You first look at the series of absolute values. Do that first. And what's going to happen? The series of absolute values either converges or it diverges. If it converges, if that's the answer, that it converges, then you get absolute convergence right away. Because if it converges, remember, if the series of absolute values converges, then the original series, the series of a sub n's, has to converge also. That was the very first theorem I wrote down in lecture today, that if a series converges if its series of absolute values converges. So if we look at the series of absolute values first, and we get that it converges, then we get that the original series converges also, and we get absolute convergence. Then if the series diverges, the series of absolute values diverges, then at that point, use the alternating series test. And what's going to happen at the alternating series test? You're either going to get that the series converges or that it diverges. And if it converges, then you get conditional convergence. And if it diverges, then that's your answer, that the series diverges. So this is kind of a little flow chart here, and this is how you get to answer the question of conditional absolute convergence or divergence. You first look at the series of absolute values. If it converges, then you're finished with the problem and you get absolute convergence. If, on the other hand, the series of absolute values diverges, then you go on to the alternating series test next. And if you get your answer to converge there, if the series converges with the alternating series test, then you get conditional convergence as your answer. If, on the other hand, using the alternating series test, the original series diverges, then that's your answer, series diverges. So it's a more complicated little flow chart than the original question. The original question is just, does the series converge? Ignoring whether it's conditional or absolute. Then you just use alternating series test and you can be done with the problem. All right, so let's look at some more examples of those ideas. So let's look at the sum as n goes from 1 to infinity of -1 to the n times 1 over n to the 4th. All right, that's our series right there. All right, and so now the question is conditional absolute convergence or divergence. So conditional, absolute, or diverge, right? That's our question here. So the first thing we do is we look at the series of absolute values. The series of absolute values in this problem would be the sum as n goes from 1 to infinity just of 1 over n to the 4th. And you see, this is an easy question because this is a p series. And p is equal to 4, and that series converges. And so what do we get here? We get that the series of absolute values converges. And because the series of absolute values converges, then the original series, that alternating series at the beginning, the original series, is absolutely convergent. Right, as soon as you get that the series of absolute values converges, you're essentially done with the problem. And you can just say that the original series converges absolutely. All right, so that's easy enough. So let's look at the another example. Okay, so this is the sum as n goes from 1 to infinity of -1 to the n times 1 over the cube root of n. All right, so in this particular problem, we would first, again, our question is conditional, absolute, or diverge. So first thing we do is we look at the sum as n goes from 1 to infinity of the absolute values. And so in this case, that would be this series, just 1 over the cube root of n, like that. And that is a 1 over n to the 1/3. That's a power in the denominator. And that is a p series also where p is equal to 1/3. And because p is less than 1, this series diverges. Okay, so on our little flow chart, what have we done? We have now, we've seen the series of absolute values diverges. So what that means is we do not have, all we can conclude here is we do not have absolute convergence. We do not have absolute convergence. We've eliminated that. And so the next thing we do is we go on to the alternating series test. So now we're not finished because now we're trying to decide between conditional convergence or divergence. Now go on to alternating series test. So at the alternating series test, right, you have to look at step 1 is that the limit as n goes to infinity of a sub n has got to be 0. So a sub n in this problem, because of the way the alternating series test is written, is this 1 over the cube root of n, which is 1 over n to the 1/3 power, like that. Right, that's a sub n here. So in this problem, that would be the limit as n goes to infinity of 1 over n to the 1/3, and sure enough, that is 0 because that's 1 over infinity. So I put a check mark there. I say, hey, condition 1 is satisfied of the alternating series test. Condition 2, I need to show that a sub n plus 1 is less than or equal to a sub n for all n greater than or equal to 1, let's say. All right, so in our problem, that would be to show that 1 over n plus 1 to the 1/3 is less than or equal to 1 over n to the 1/3. Now, what I'm going to do here is I'm going to look at derivatives. To me, that's in most cases, that's a little bit more straightforward. So f of x is 1 over x to the 1/3. And so f prime of x is -1/3 x to the -2/3. Or -1 over 3x to the 2/3. And sure enough, what do we have? That f prime of x is less than 0 for all x greater than 1, certainly greater than or equal to 1. And so what does that mean? That means that it's got to be true that a sub n plus 1 is less than or equal to a sub n for all n there. And so that's checks also. So what do we have? By the alternating series test, the original series converges. And so what do we have? We have that the original series converges, but the series of absolute values diverges. And that was the first part of the problem. And so this gives us conditional convergence. All right, so the alternating series test showed that the series converged, but the series of absolute values diverge, and so you got to get conditional convergence in a problem like this. All right, so let's see. Let's look at, as an example, let's look at, this is problem number 262. Something maybe a little bit different. So this is on section 5.5, number 262. Let's have a look at that problem right there. This is the sum as n goes from 1 to infinity of -1 to the n plus 1 times the natural log of 1 over n, like that. So here's our series, like so. And so we first look at the series of absolute values. So the series of absolute values is this series right here. The sum as n goes from 1 to infinity of the natural log of 1 over n. Right, and so, the question would be, what does that series do? Well, if you think about this for a second, if you just look at the limit of the nth term there, the limit as n goes to infinity of the natural log of 1 over n, this is the natural log of something going to 0, and so that's actually negative infinity. And so this series diverges, and really you get that the original series has got to diverge also, and you could really just use the nth term test for divergence here, and you could say that the original series diverges also. So the original series must also diverge. You could go on to use the alternating series test, but you don't really need that here. So I would just say by the nth term test for divergence, because the nth term of the original series doesn't even go to 0. So I would be okay with you saying that. You have to show me that nth term is not going to go to 0, but that's certainly got to be the case that the nth term isn't going to go to 0 here. All right, so you get that this series diverges. So over the last few problems, we've looked at one that converges absolutely, one that converges conditionally, and one that diverges. All right, so you're getting several examples of several different things here. All right, let's see. So that finishes up what we're going to do. Well, let's see. Let's look at one more problem. That's what I'll do. Yeah, I was just hesitating there a little bit. So let's look at number 264. You have the sum as n goes from 1 to infinity of -1 to the n plus 1 times n squared over 1 plus n to the 4th. All right, so we want to see whether this is conditional, absolute, or just diverges. So we first look at the series of absolute values. And the series of absolute values in this problem would be the sum as n goes from 1 to infinity of n squared over 1 plus n to the 4th. And that series, you can show, in this series, you compare, this is a good example of a comparison problem. Compare this series to the sum as n goes from 1 to infinity of 1 over n squared, which is a convergent p-series. Right, because p is equal to 2. And so what I'm using here is limit comparison. So you take the limit as n goes to infinity of 1 over n squared and compare that to n squared over 1 plus n to the 4th. And so that gives you the limit as n goes to infinity of 1 plus n to the 4th over n to the 4th when you invert and multiply there. And that limit's equal to 1. So by limit comparison, since the series 1 over n squared converges, then the series of absolute values, the series n squared over 1 plus n to the fourth, converges. And remember, this is the series of absolute values. So what did we just show? That the series of absolute values converges. And so that gives us absolute convergence. All right. So if we can show that the series of absolute values converges, then we get absolute convergence in the problem. All right. So we are now that's all we're going to do with the alternating series test. Now, the alternating series test is actually one where you can bound the error on the series. You know, because if you can show a series converges, you're not showing what it converges to. So let me just briefly talk about bounds on the error for alternating series. I am not going to hold you responsible for this on a test. If you'll look, this is not on the review for exam 3. However, if you look at this series, the sum as n goes from whoops, be nice if I wrote it right. Look at this alternating series. The sum as n goes from 1 to infinity of -1 to the n plus 1 times 1 over n cubed. All right, so this series converges absolutely. The series of absolute values converges. I'd let you go through that on your own. So this series converges. Absolutely. Now remember what convergence means ultimately is that the series has a sum, right? And in this case, since it's absolute, it means the series has the same sum no matter how you rearrange it. But ultimately, it means the series has a sum. Notice we're not finding what the sum is. We're just saying that it has a sum. So if you wrote out, if we look at the sequence of partial sums, right, if that's what we're looking at, and let's look at the third term of the sequence of partial sums, the third term of the sequence of partial sums. So that would be add S1 plus S2, I'm sorry. That would be add A1 plus A2 plus A3. Add the first 3 terms. So the first term of the sequence of partial sums would be -1 squared times 1 over 1. Plus the second one would be -1 cubed times 1 over 2 cubed. This is cubed here. And then the next one would be -1 to the fourth, right? That's when n is 3, times 1 over 3 cubed. So what do we get there? We get 1 minus 1/8 plus 1/27, like that. 1 minus 1/8 plus 1/27. And let's see, so that would be, if I do the arithmetic there, 1 minus, I'm just going to do that real quick here. I get 197 over 216. 197 over 216. That answer, this sum, must be within, what you do is you go out to the fourth term of the sequence of partial sum, I'm sorry, the fourth term of the series, and a sub 4 has to bound the error on this. So a sub 4 bounds the error on this sum. what that means is if you look at a sub 4 is going to be, 1 over 4 cubed, or 1 over 64, like that. And so what you're saying here is that 197 over 216 must be within 1 over 64 of the actual sum. So it's pretty close. In other words, the next term always bounds the error. So for S sub 8, then A sub 9 bounds the error on that. It's always the next term of the series. So obviously, as you get deeper and deeper into the series, you're getting a better and better approximation for the sum. All right, so I just briefly wanted to talk about that. We're definitely not going to get into it any more than that, okay, just so you know. All right, so let's see. We're doing good here. So what I want to finish the class today with is the ratio test, a powerful test for looking at, and the ratio test applies whether you have an alternating series or a non-alternating. It doesn't matter. So it applies to alternating and non-alternating. So alternating and non-alternating. And this is good. It works really nicely good for a series with factorials and exponents. And it goes like this. If we're given this we're given this infinite series, the sum as n goes from 1 to infinity of a sub n, one of three things has to be true here. That the sum converges absolutely, means that no matter how you rearrange it, you always get the same sum if the limit as n goes to infinity of the ratio of successive terms, a sub n plus 1 divided by a sub n, is less than 1. You get absolute convergence in that case. The sum as n goes from 1 to infinity of a sub n diverges if the limit as n goes to infinity of the ratio of successive terms here is greater than 1. And finally, the third possibility here is that if the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n is equal to 1, then the test is essentially fails. The test is inconclusive. In other words, you can't tell whether you have convergence or divergence. All right, so what we're going to do is we're going to just finish the day today by looking at some examples of the ratio test. All right, so we're going to jump right into this. Here's the ratio test right here. And so we're going to look at a series. Sum as n goes from 1 to infinity of e to the negative n power times n factorial. So right away we get a series that has a factorial in it. And you have the sum as n goes from 1 to infinity of n factorial over e to the n, if you want to look at it that way. All right, so what we're going to do is we're going to use the ratio test on this problem. So we look at the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n, like that. And so that would be the limit as n goes to infinity of a sub n plus 1, which would be n plus 1 factorial over e to the n plus 1. And that would all be divided by n factorial over e to the n. Now, most of the time with the ratio test, you're going to get kind of a yucky fraction right here, but this is going to simplify exclude a lot here. And by the way, all these numbers in here are positive. There's not any alternating aspects to this series. None of the terms are negative, and so I can drop the absolute values here pretty much. And so you have the limit as n goes to infinity, or you can keep them, by the way, it doesn't matter. So you have e to the n times n plus 1 factorial. So I'm inverting and multiplying here, divided by e to the n plus 1 times n factorial. Now you have to get good at the algebra here in this kind of problem. You have the limit as n goes to infinity. The e's, I have n e's in the numerator and n plus 1 e's in the denominator. And so I'm left with an e in the denominator. And then the factorials, I've got n plus 1 factorial over n factorial. And we've talked about that kind of arithmetic earlier in a couple of lectures ago. But n plus 1 factorial divided by n factorial, all the factors cancel except for an n plus 1 in the numerator. And so you're left with just n plus 1 over e. And you're taking the limit as n goes to infinity. And now look where the n is. The n is in the numerator. E is a constant. So this goes to infinity. And so how can we finish this? We can conclude at the end by the ratio test this series diverges. All right, by the ratio test, this series diverges. All right, because you got an answer bigger than 1. All right, let's look at another example. All right, so the next example, we have the sum as n goes from 1 to infinity of negative 1 to the n plus 1. So this one is an alternating series times n squared times 2 to the n over n factorial. Wow. Like that. So it's a complicated expression, but it does have a factorial and powers in it. And so I'm going to use the ratio test here, definitely. All right, so now because you've got these absolute values, right, that factor of negative 1 we can ignore because it's going to become positive. So we're looking at, so we can ignore that, which is nice. So we have the limit as n goes to infinity of a sub n plus 1 over a sub n. And that factor of negative 1 at the beginning, you know, sometimes it's negative, sometimes it's positive, but since it's absolute values, we can ignore it. So we don't have to worry about it here. That's good. I'm going to keep the absolute values because it's a convenient grouping symbol. So you have n plus 1, you have a sub n plus 1. So that'd be n plus 1 squared times 2 to the n plus 1 over n plus 1 factorial, all divided by n squared times 2 to the n over n factorial. Now take your time on the algebra on a problem like this. It's easy to make an algebra mistake. Remember, you're inverting and multiplying. So when you invert and multiply, you know, you're going to take the outside 2 and multiply them, and you're going to take the inside 2 and multiply them. All right? The outside 2 is going to be your numerator, and the inside 2 is going to be your denominator. So take your time when you do this. So you have the limit as n goes to infinity. I certainly would not do any canceling at this point. I just write this as n plus 1 squared times 2 to the n plus 1 times n factorial. That's our numerator. And then the denominator would be, and I try to line up the factors here also, the like factors here. So that's n squared times 2 to the n times n plus 1 factorial. Like that. All right, so when I go through and I divide out factors, right, and common factors there, what happens here? Well, on the 2's, I'm left with a 2 in the numerator because there's n plus 1 2's in the numerator and n 2's in the denominator. So I'm left with a 2 in the numerator. With the n factorial and the n plus 1 factorial, I'm left with an n plus 1 in the denominator, like that. And then what else have I got left? Well, I've got the n plus 1 squared, and then I have an n squared, like that. And then notice here I've got an n plus 1. I still have a little bit of canceling to do because now I have an n plus 1 that's common. And so I cancel one of those, and I'm left with 2 times n plus 1 in the numerator, and in the denominator I'm left with n squared because I canceled one of those n plus 1's there. And notice on this expression, the degree of the numerator is smaller than the degree of the denominator, and so I get 0 as the answer here. And so what's our conclusion? Because I get 0 by the ratio test, this series is actually absolutely convergent, not just convergent, but absolutely convergent. All right, so the ratio test worked fairly well there. All right, we've got probably one more problem to do with the ratio test, and then I think we will be finished for the day. All right, so on this problem, so this is not going to be a trivial problem at all. You have the sum as n goes from 1 to infinity of n factorial over n to the n. All right, and so because I've got that factorial in here, using the ratio test makes sense. But it doesn't quite work out quite as smoothly as we might hope. So you look at the limit as n goes to infinity of the n plus first term compared to the nth term. And so let's just go ahead and invert and multiply right away here. So the n plus first term would be n plus 1 factorial over n plus 1 to the n plus 1. And that'd be multiplied by the reciprocal of a sub n, right? And so that would be n to the n over n factorial, like that. Okay, so what that gives us is the limit as n goes to infinity. The n plus 1 factorial and the n factorial divide out and leave me with an n plus 1 in the numerator. And then I have a n to the n in the numerator still. And then in the denominator, I have n plus 1 to the n plus 1. And so notice in this problem, I get an n plus 1 that's common. I can cancel one of those out. And so this leaves me with the limit as n goes to infinity of n to the n over, if you're canceling one of those n plus 1's, I had n plus 1 of them in the denominator. So I'm canceling one of them, and now I have one of them, or n of them in the denominator. So I get that expression right there. Or finally, we could write this as the limit as n goes to infinity of just n over n plus 1 to the n. And, the inside, the base there goes to 1, but the exponent goes to infinity. And so you end up with an indeterminate form. And so what we're going to do here is we are going to try to see if we can use L'Hopital's rule. And so remember how you do this with an exponential indeterminate form like this. You have to use logarithms. So you use logs here. And so you let y be this limit. Like that. So you let y be the limit. And then you take the natural log of both sides. Like that. And then you interchange the limit and the log. because you can do that because this natural log is a continuous function here, like that. And then you bring down the n as a factor, like so. And this expression right here is now infinity times 0, because that's the natural log of 1 as n goes to infinity. So that's indeterminate. So you have to write it, if you want to use L'Hopital's rule, you have to write it kind of crazy here. What we do is we write this as the natural log of n over n plus 1 in the numerator, and in the denominator you put 1 over n. You know, multiplying by n right here is the same thing as dividing by 1 over n. And that actually gives you 0 over 0. And believe it or not, that gives you a L'Hopital's rule situation right there. So, okay, so let's see. So what do we get here? This is kind of messy. So you have the natural log of y equals the limit as n goes to infinity, the derivative of the natural log of n over n plus 1, which I would say is 1 over n times n plus 1. 1 over n plus 1, like that. And so that's the reciprocal of that expression. So that's n plus 1 over n. Let me kind of write that a little bit higher there. So that would be n plus 1 over n times the derivative of n over n plus 1, which is actually the quotient rule. Oh my gosh. So you have n plus 1 times 1 minus, that's the bottom times the derivative of the top, minus the top times the derivative of the bottom. So that'd be n times 1, all divided by n squared. So that's the derivative of that logarithm in the front. It's 1 over u. That's where I get this reciprocal right there. And then you have to take the derivative of u, which is the quotient rule. And that would all be over the derivative of 1 over n, which is negative 1 over n squared. So you get a really kind of crazy expression here. So this is the natural log of y equals the limit as n goes to infinity of, let's see what we've got here. This is going to be n plus 1 over n times, and in that little quotient rule expression there, you have an n minus n, so that's 0. So you're left with 1 over n squared. And that's all over negative 1 over n squared, like that. All right, so, you know, we're kind of making progress here. So you have the natural log of y is equal to the limit as n goes to infinity. In the numerator, this would be n plus 1 over n cubed over negative 1 over n squared. And so that would give us the natural log of y is equal to the limit as n goes to infinity of n cubed plus n squared in the numerator divided by n cubed, and that would all be negative, right? Like that, because there's a negative 1 in there. And believe it or not, you know, the degree in the numerator and the denominator are the same, so that goes to 1, and so you end up with the natural log of y equals negative 1. And so y, finally, you get y, which is our limit, is e to the negative 1, or 1 over e. And so the value of the limit here is 1 over e. So I'm going to put this conclusion here kind of in a little box right here in the middle of the page. So what do we get here? That the limit is n, let's step back for a second. The limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n ended up being 1 over e, or e to the negative 1, which is, you know, certainly a fraction less than 1. And so because you get that value, we know that the series converges, and it converges absolutely. That was a messy problem, right? A lot of work to do to evaluate the limit on this. And the reason why this one was hard is because the limit, as n goes to infinity on this problem, was difficult to evaluate, right? The last couple of problems, that limit wasn't so bad to do. This one was a mess to do. All right, so let's see. That's what I'm going to do for the day today. So when we come back, so next week, just so you know, first of all, Sunday, April the 15th, a few problems from the series worksheet will be due for a grade for your homework. A few problems from the series worksheet due. And I will email you, or I will send you a remind message on Saturday. So a remind message, so you should be working on that sheet, because all those problems are good review problems for the test. But a remind message on Saturday, and I will tell you which ones to turn in as to which ones. All right, and then on Monday, April the 16th. Oh, and by the way, I also, let me erase that real quick. Here, I also have online office hours on Sunday. Might as well write that in there also. Online office hours, 8:30 to 9:30 p.m. Please stop by if you have some questions. On Monday, April the 16th, we have live lecture. It's back at 7 p.m. at the regular time that I'll post it. So that'll be at 7 p.m. And then on, let's see, on Tuesday, I'll be online again from both 11 to noon and 8:30 to 9:30. Wednesday, no lecture. Right, I'll be on campus that day. Come by for help. I'd be happy to help you out. And then on Thursday, finally, exam 3's window opens. So exam 3 opens on that day. And I'll also be on campus that day as well. So you have lots of times when you can come by and talk to me and get some help. I'll be happy to help you out. Don't forget that sometimes I can make appointments for online office hours also. So don't forget that as well. All right, so let me know if you need any help. Good luck as you prepare for exam 3. And we will move on. And by the way, one thing I didn't mention is that on Monday, the live lecture, we're going to introduce Power Series and Taylor Series. And we're going to start finishing up what we're going to be doing with sequences and series gradually. All right, so everybody have a good rest of your week. Let me know if there's any way I can help you. Have a good one. Thank you.